Hi everybody, my name is Bahador. The title of the talk that I'm going to be presenting is the first comparative characterization of multi-cloud connectivity in today's internet. This is a collaboration between me, Ram, Reza, and Walter. Within today's internet, enterprises are increasingly employing multi-cloud deployments, with recent reports indicating that about 84% of enterprises are leveraging more than one cloud provider. Within this multi-cloud setting, enterprises pick and choose cloud services from multiple cloud providers and establish end-to-end connectivity between their cloud resources and their on-premise resources. Examples of this would be Hulu and Netflix, which have deployments within both AWS and GCP regions. There are many benefits associated with multi-cloud deployments. First and foremost, it allows them to avoid vendor lock-in where they are tied down to a single cloud provider. It allows enterprises to benefit from exclusive service offerings of each cloud provider, and they could leverage the different geographic regions of these cloud providers and have a wider geographic footprint. And lastly, they could reduce their operational costs by benefiting from the cheaper alternatives of different cloud providers. This multi-cloud adoption has fueled the expansion of cloud providers' network footprint and cloud connectivity options. In terms of the connectivity options, I'm going to be using this high-level figure to illustrate the different options that are available. So on the right-hand corner, we have an enterprise network. This enterprise network is leveraging regions of AWS and Azure. In terms of connectivity, they could utilize the backbone of these cloud providers, or they could go to the public internet where they basically are going through different transit providers. And lastly, they could leverage the backbone of third-party connectivity providers such as DataPipe, Hop1, and Megaport. There are many challenges associated with multi-cloud deployments. The performance characteristics of different connectivity options are not known. And furthermore, the effects of routing policy, geographic footprint, peering point, and network conditions on multi-cloud connectivity performances have not been studied. So this paper presents a third-party cloud and enterprise-centric measurement study aimed at characterizing the performance of multi-cloud connectivity options. The remainder of my talk would have the following outline. First, we would touch on our measurement methodology, both in terms of our deployment setting, how we establish cloud-to-cloud connectivity, and how we collect our data, what metrics we are interested in. Afterwards, we would present the characterizations of these cloud-to-cloud paths in terms of latency, path, and throughput. Lastly, we'll have a short discussion on some other measurements that we performed but we didn't have a chance to present due to brevity and shortage of time. And lastly, we'll end this talk by going over a couple of key takeaways. So in terms of deployment, we limit our focus to a representative multi-cloud deployment within the US. We target the top 3 cloud providers, in other words, AWS, Azure, and GCP on both coasts of the US. So 6 regions in total, and within each of these regions we deploy a virtual machine. For CPP and best effort public connectivity, we don't have to do anything. These are facilitated by the default routes that are set up by the cloud provider networks. For TPP connectivity, we limit our focus to one of the top third-party connectivity providers. This is mainly due to cost, to give you a sense of how expensive deployment within these third-party connectivity providers are. A single 1 gigabit per second link would cost about $1,000 per month. So by leveraging the backbone of one of the top third-party connectivity providers, we deploy virtual routers on both coasts, and we establish BGP sessions between these virtual routers and the border routers of cloud providers. So now we can have our own private network. And we interconnect each of these regions to these virtual routers using 50 megabit per second links. For data collection, we perform pairwise measurements between all CP regions across all connectivity options, so 60 pairs in total. And we perform our measurements both within a region, inter-region, and across region or inter-region. These measurements were performed for about a month in the spring of 2019, and we repeated our measurements in 10-minute periodic rounds. So for each metric we have about 48K samples. Within each round we were interested in latency, path, and throughput measurements. For latency, we relied on 10 consecutive ping probes. For path, we performed 10 ICMP Paris trace routes. And for throughput, we performed 10 consecutive seconds of TCP using iPerf3. We discarded the first 5 seconds of these throughput measurements to account for TCP's slow start. Lastly, we annotated the hops of our traceroute measurements with their corresponding ASN and ORT numbers by using the best practices. And we checked the existence of IXP hops along the path by relying on CADA's aggregate IXP dataset. So in terms of characteristics of these cloud-to-cloud paths, the first characterization that we present is the latency of these paths. For our representation of our measurements, we rely on figures that you see on the right-hand side of this slide. There's a lot of information packed into this figure, so I'm going to break it down. So we have 3 rows within these figures corresponding to the source cloud provider that was performing the measurements. So we have AWS, GCP, and Azure. Within each row we have 2 columns. The left-hand side corresponds to intra-region measurements, and the right-hand side corresponds to inter-region measurements. Within each of these figures, we have color codings corresponding to different connectivity options. Blue for CPP, orange for TPP. You might be wondering why we don't have a color coding for public internet. We'll discuss that later on. And each of these columns have a label which corresponds to the path. So for this example, we have a source of AWS within California going to a region of GCP within California. So there are a couple of things that are worthy of highlighting. The first thing is that the median of latency between AWS and Azure across within each coast is about 2 milliseconds. While The median of latency between GCP and AWS or Azure within California is about 13 milliseconds. This is in accordance with their geodistance of the data centers. So within California, AWS and Azure have data centers within Northern California, while Google's data centers are in Southern California. And coast-to-coast latency is about 60 to 70 milliseconds for different paths. Overall, across all of paths, we consistently see that CPP paths have lower medians of RTT and less variability, which is indicative that CPP paths are outperforming their TPP counterparts. Which begs the question that why do CPPs outperform TPPs, given the paid nature of these third-party connectivity providers? To answer that, we dug into our data, and the first thing that we looked into was our traceroute measurements. So when we looked at this data, we basically measured the number of organizations that we see along the path. The figure on the right hand side is presenting the fraction of organization numbers we saw along the paths. For intra-CP paths or measurements, we observed only a single organization corresponding to the cloud provider network. So the measurements always remained within the cloud provider's network. For cross cloud provider paths, we observed that 96% of them remain within the source and destination cloud provider networks. And for the remaining 4% of paths, they correspond to paths that were going through direct peerings between these cloud provider networks facilitated by an IXP. Overall, we didn't observe any change in AS path during the measurement time frame, which again is in contrast to route asymmetry and flapping in the public internet. Collectively, these observations indicate that the backbones of these major cloud providers are tightly interconnected with each other. The next characteristic that we looked into was the routing model of these cloud providers. For that, we relied on border mappet to infer the peering hop along each path. The latency of this peering hop is indicative of whether the cloud provider is utilizing hot or cold potato routing. So the figure on the right hand side is presenting the distribution of this peering hop. For AWS, we observe that they are always utilizing hot potato routing. In other words, they're handing off the traffic as close as possible to the source region. For GCP, we observe that they always utilize cold potato routing, and these bimodal distributions that you see correspond to the RTT difference between regions of GCP and AWS across each coast. Lastly, for Azure, which was the most interesting case of all three, we observed that they have a mixed routing policy where they have hot potato routing for GCP, while they have a mix of hot and cold potato routing for AWS. So for measurements within the same region, we saw that they are using hot potato routing. This indicates that AWS and Azure do have peering points within the same region. But when Azure was targeting another AWS region within a different region, we observed that they are performing cold potato routing, where they're carrying the traffic closer to AWS. Again, this bimodal distribution that you see corresponds to different handoff points. For the majority of inter-region paths, the traffic was handed off in Dallas, Texas, while some fraction of the paths were being handed off in Atlanta, Georgia. We suspect that this mixed routing policy of Azure has something to do with the dominance of AWS, where they were able to negotiate how Azure routes traffic towards their network. The next characteristic that we present is the throughput for these cloud-to-cloud routes. Again, we're using the same representation for our measurements on the right-hand side of this slide. Overall, we observe higher median and less variability for throughput of CPP routes compared to their TPP counterpart. And we also observe higher variability of throughput for TPP routes within inter-region measurements. Within our measurements, we observe that the higher the variability, the higher the median of RTT we had. So there was a direct correlation between higher medians of RTT and more throughput variability. Again, these observations raise the question of why are CPPs outperforming TPPs? And to answer that, we looked into the loss rates of these cloud-to-cloud paths. We approximated loss rate by relying on our latency probes. Basically, an unresponsive latency probe was indicative of a packet loss, and we approximated loss rate to be about 0.1 and 0.01% for TPP and CPP routes, respectively. Plugging in these loss rate numbers into Matisse et al.'s TCP throughput model, using a maximum segment size of 1460 bytes and a latency of 70 milliseconds, gets us a throughput of about 53 megabit per second, which is bordering our link capacity of 50 megabit per second. So a burst of packet losses could lead to a subpar throughput. To have a better understanding of the dynamics of this loss rate, we modified our probing mechanism to include more fine-grained measurement of loss rate. So for that, we added 5 seconds of UDP throughput measurement using iPerf3, but we source limited these throughput measurements to 50 megabit per second. So in ideal setting, we would observe 0 packet losses. And these throughput measurements were performed for a full week. First thing to note is that we observe 0 out-of-order packets using these measurements, and our overall loss rate using these finer grain measurements was higher than our earlier approximations. We estimated, we measured them to be about 0.5 and 1% for CPP and TPP routes. Another interesting observation that we had was 76% of our sampling periods for CPP routes observed 0 packet loss, while for TPP routes this was only 37% of our sampling periods, which indicates that packet losses are more prevalent and commonplace within TPP routes, while for CPPs it seems to be more of a bursty nature. This bursty packet loss could be detrimental for streaming applications. The right-hand figure is again the distribution of these loss rates using the same format that we had. A couple of interesting observation over here is we observed that intra-paths of California have higher loss rates compared to Virginia, and paths for TPP paths that are destined to California, we observe an asymmetrically higher loss rate to their inverse path, which indicates that the ingress port of our California router within the TPP network is congested. Lastly, we wanted to have a discussion on some other measurements that we performed but couldn't present due to brevity. Motivated by the observation that cloud provider networks are tightly interconnected with each other, we performed the same measurement on a global scale. So we deployed virtual machines within all global regions of these top 3 cloud providers and performed pairwise path measurements. Again, we observe that we only see the source and destination cloud provider networks within our paths, with the exception of a couple of paths that had IXPs along the way. But even for those, the endpoints of these interconnections were both the source and destination cloud providers. The next thing was we observed that cloud providers handle path measurements heterogeneously. So for GCP, for example, they do not expose any of their internal routers within trace routes unless the destination of the path measurement is within GCP. Similarly, Azure also didn't expose any internal routers, but they did respond for their border routers that were peering with other cloud providers. And AWS was the only cloud provider that relied on multiple ASNs for their cloud network. We also performed some enterprise to cloud measurements, and within those measurements we outlined some possible use cases where you could benefit from utilizing third-party providers' network. The details of that are available within the appendix. So with that, I wanted to conclude my talk with a couple of key takeaways. Within multi-cloud settings, there are a wealth of connectivity options, including CPP, TPP, and best effort public internet. For enterprises, paid services do not necessarily achieve better performance, and cloud backbones are well provisioned and tightly interconnected with each other, which make them ideal for cloud-to-cloud deployments. And lastly, enterprises should consider various factors for end-to-end performance, including the geographic region of the cloud provider, the routing policy, as well as the location of the peering point. So I wanted to thank all of you for listening to this presentation, and with that, I would conclude my talk.